All right, welcome back to lecture 2 of acid-base chemistry. In lecture 1, we looked at kind of some general aspects of acid-base chemistry, and towards the end we established that acid-base reactions are always going to favor the weaker acid-base pair. And in order to assess the acidity of a molecule, we really need to look at the conjugate base of that acid, not actually at the acid itself. And so today, in today's lecture, we're going to investigate how different structural features of a molecule will influence the acidity of that molecule. And so there are going to be 7 different things that we go over. All right, and I just want to start out today by looking at these 2 molecules. All right, so on the right here, we have an alcohol. So this is just propanol, so 3 carbons and OH. And then on the left, we have a carboxylic acid. This is propanoic acid. Right? You can see the only difference between these is that the alcohol has an sp3 hybridized carbon next to the oxygen. So there are 2 hydrogens on that carbon. And the carboxylic acid next to the oxygen that's going to lose a proton, there's a carbonyl. Right? You can see that the carboxylic acid has a lower pKa, so it's going to be more acidic. Alcohol has a higher pKa, so it's going to be less acidic. All right, and so whenever we're assessing which of these 2, if we didn't know the pKa's and we had to look at these and try to assess which is more acidic, we're not really going to look at the acids, but we're going to look at the conjugate bases. All right, and so whenever this proton is lost, the electrons in the sigma bond will be isolated or come back to oxygen. Right, and so the electrons from the sigma bond end up here. On the alcohol, it's kind of the same thing. When that sigma bond is broken, the proton is taken away. The electrons from that sigma bond go on to oxygen. And so we have to be able to look at these electrons, this non-bonding pair, and understand what they're doing in that molecule and whether the molecule can do anything to help stabilize those electrons. Right? Obviously, because this is more acidic, that means that the conjugate base is going to be more stable, right? And this being less acidic means that the conjugate base is going to be less stable. So when we compare these 2 conjugate bases, particularly the electrons that are left behind after the proton is pulled, we can say that these electrons are less stable, higher energy electrons. These electrons are more stable, lower energy electrons, right? And it should make sense that the acid that forms a stable product is going to be somewhat willing to give up that proton, right? Whereas the acid that forms a less stable or high energy product or conjugate base is not going to be able to give up a proton very easily. Okay, so let's get into this. So the first factor that we're going to talk about is electronegativity. And so how does the electronegativity of an atom affect the acidity of the protons attached to that atom? Right, so you can see here I have 4 different acids. Right, I'm not, I think when you learn about acids, you're typically learning about hydrogen chloride, acetic acid, right? Things that we commonly think of as being acidic. Technically, any molecule with a proton qualifies as an acid, right? It might be very reluctant to give up that proton, but as long as it has a proton, it qualifies as an acid. All right, so methane we don't consider an acid, but there are 4 protons attached to that carbon, so technically it can act as an acid under the right conditions. All right, so when we look at these, you can see that the atom that is giving up the proton, carbon, nitrogen, oxygen, and fluorine, the relationship between these atoms is that they are all second-row elements, and they're all in order going from left to right. Okay, carbon is going to be the least electronegative of these 4 atoms, and fluorine is going to be the most electronegative. Now I said when you assess the acidity of a molecule, you're not looking at the acid, right? But you're really thinking about the structure of the conjugate base and the stability of the electrons that are left behind after the proton is pulled. All right? So whenever a proton is pulled from methane, that lone pair ends up on carbon, and carbon adopts a formal negative charge, right? With ammonia, NH3, whenever one of those protons is pulled, the electrons come back and sit on nitrogen as a non-bonding pair. With water, again, the sigma electrons after the proton will be pulled. will be sitting on oxygen, and then with hydrogen fluoride, those electrons will sit on fluorine. The electronegativity of the atom that accepts those electrons is going to influence the stability of those electrons. So we would imagine that a pair of electrons on fluorine would be much more stable than a pair of electrons on carbon. And this really comes down to the electronegativity of fluorine and the ability of fluorine to pull those electrons in close to the nucleus, right, relative to carbon. Because these electrons are going to be pulled a little closer to the nucleus, they should be more stable, right? Carbon is going to be a little more promiscuous with its electrons. They're going to float a little farther away from the nucleus, and so they won't be as stable. And we can see that in the pKa trends here, right? As the electronegativity of the atom increases, the atom holding the electron pair, right? As the electronegativity increases, the pKa is also, or the acidity is also going to increase, so the pKa will drop. Right? So HF is going to be the most acidic, water second most acidic, ammonia third most acidic, and then methane is going to be the least acidic. Right? And so it all comes down into how well those electrons are stabilized after the proton is pulled. Right? The second factor that we're going to go over is polarizability, right? Which really, when we're talking about polarizability, we're talking about the size of the shell, or the size of the orbital that the electrons will be in after the proton is pulled, right? So you can see here we're investigating the hydrohalic acids, right, or the halogen atoms attached to a hydrogen, right? So we have HF, HCl, HBr, and HI. And when I drew these molecules, I tried to draw them in a way that gives you some information about the bond length between the halogen atom and hydrogen, right? With fluorine hydrogen bond being the shortest, iodine hydrogen bond being the longest. But what this really gets to is the size of the orbital that the electrons will sit in after the proton is pulled, right? So fluorine is going to be in the second row of the periodic table, and so it uses the 2s and 2p orbitals in that second row. Chlorine's in the third row, so it's going to be using the 3s and 3p orbitals. Bromine's in the fourth row, and so it will use the 4s and 4p orbitals. And iodine's in the fifth row, so it uses the 5s and 5p orbitals. Obviously, or hopefully you realize that the 5s and 5p orbitals are going to be much larger than the 4s, 3s, and 2s, right? The fifth shell is going to be much larger than the fourth shell, third shell, and second shell. So if you're a pair of electrons that are left behind after a proton is pulled, it's actually better to be in a bigger shell, even though those electrons are going to be farther from the nucleus, right? In a bigger shell, those electrons are going to be able to spread out away from each other, right? And since you have two electrons both negatively charged, those two electrons tend to repel each other, and the closer, or the smaller orbital that they're held in, the harder it is, or the more energy they will have when they try to repel each other, because they can't get that far away from each other, right? So electrons left behind in, say, a 2sp3 orbital on fluorine are going to be contained to a very small space, whereas the two electrons left behind in a 5sp3 orbital on iodine are going to be in a very large space. So those electrons can spread out, get away from each other, and become lower in energy. Right? You might be looking at this and saying, well, this runs counter to the electronegativity trend, right? And that's true, right? Fluorine is going to be the most electronegative, iodine is going to be the least electronegative. So when we're thinking about electronegativity trends, we're only thinking about a single row across the periodic table, right? So electronegativity is only going to work if we're looking at row 2, right? Or comparing atoms in row 2, or if we're comparing atoms that are only in row 3, right? Going up and down on the periodic table within a column, right? That's when we're talking about polarizability, and that has a different effect, right? So as we go across on the electronegativity table, or on the periodic table, we have to pay attention to electronegativity. As we go up and down on the periodic table, we have to pay attention to the polarizability of the atom. All right, third factor is going to be the hybridization of the atom that's gaining the electron pair from the sigma bond to hydrogen. All right, so here we have three molecules, all 2 carbons. So ethane, ethene, and ethyne. Right? Ethane is going to have sp3 hybridized carbon. Ethene will have sp2 hybridized carbons. And ethyne is going to have sp hybridized carbons. Right? Whenever this proton is pulled, the electrons that are left behind will be isolated to an sp3 orbital. This proton, if it's pulled, the electrons left behind will be isolated to an sp2 orbital. And with this proton, when it's left behind, or when it's pulled, the electrons that are left behind will be isolated to an sp orbital. Right? If we think about the makeup of these orbitals, right? I mean, to some of you, this might seem just like a code, but it's really telling you what orbitals are hybridizing. Right? We have one s orbital and then 3 p orbitals. Here, there's one s orbital and 2 p orbitals. Here, there's one s orbital and 1 p orbital. So an sp3 orbital is 25% s and 75% p, right? So 25% of the sp3 orbital has s character, right? And the other 75% is p character. If we look over at sp orbitals, right? sp orbitals, half of that sp orbital is from an s orbital, right? Half of that sp orbital is from a p orbital, right? Overall, the 2s orbital is lower in energy than the 2p orbital. So it would seem to make sense that an orbital with more s character should be a little closer to the nucleus, have more s character, and therefore be lower in energy. Right? And so what we see in the pKa trend is that whenever this proton is pulled, these electrons are going to be left behind in an sp orbital. They should be more stable than when this proton is pulled, and these electrons are left behind in an sp3 orbital. And in fact, that's what we see in the pKa trend, right? With these electrons being the least stable, and so the pKa being the highest, and this molecule being the least acidic. All right, and then if we move over to ethyne, okay, when those electrons are left behind in an sp orbital, they're relatively stable. pKa is going to be 25, right? pKa is lower than it is over here, and so this is going to be the more acidic molecule. Right? So again, it's just depends upon the stability of the electrons that are left behind whenever the proton is pulled. All right, and then we're going to look at formal charge. Okay, so here are 2 different examples. Here's an example where we have a nitrogen, right? You can see this nitrogen has 4 bonds to hydrogen, whereas this nitrogen has 3 bonds to hydrogen, right? You can see here we have a formal charge. Over here, this nitrogen is neutral with a non-bonding pair. This will be the most acidic of the 2. This will be the least acidic of the 2, right? Lower pKa and higher pKa. All right, and so when we're looking at 2 molecules that are essentially the same, except one has an extra bond and a formal charge, this will always be the more acidic of the 2 molecules, right? And if we think about this or on a slightly more qualitative level, right, you can imagine in order for this nitrogen to make 4 bonds, it's given away its non-bonding pair of electrons. And so it's pulling hard on all of these bonds in order to get those non-bonding electrons back. If we deprotonate ammonium, this molecule here will end up with ammonia. And so we'll go from a charged molecule to a neutral molecule, right? If we deprotonate ammonia, right, pull a proton off of this nitrogen, which is neutral, we'll go from a neutral molecule to a molecule with a formal negative charge, right? As a result, this is going to be the more acidic because if we lose a proton, we'll get to a neutral state. This will be the less acidic because if we lose a proton, we'll get to a charged state. Right? Same thing with hydronium and water, right? Hydronium has given away a pair of electrons in order to make a 3rd bond, has a formal positive charge. If we give away that proton, it will regain its non-bonding pair and will become neutral. So if a proton is lost, this will return to a neutral state. Here in water, if a proton is lost, it will go to a charged state with a negative formal charge. Okay, the one that will return to a neutral state has a lower pKa, is going to be more acidic, right? The one that will change to a charged state has a higher pKa and will be less acidic. Right, the fifth factor is going to be the resonance delocalization of the electron pair that's left behind after the proton is pulled. Okay, and so this kind of gets us back to the example at the beginning of this lecture where we're looking at a carboxylic acid versus an alcohol. Okay, and again, the only difference here is that the carbon next to the hydroxy group in the carboxylic acid is a carbonyl, or has a carbonyl as part of a carbonyl, whereas the carbon next to the hydroxy group in the alcohol is sp3 hybridized and it has two hydrogens. When a proton is lost from the carboxylic acid, the lone pair ends up on this oxygen, but hopefully at this point you realize that this lone pair is in conjugation with this pi system that's part of the carbonyl. Right? And so we can draw a resonance structure that shows that these electrons are not just sitting on this oxygen, but are being shared among these three atoms, right? They can be delocalized into this pi system. And so because they are spread out over a larger volume of space, those electrons are going to be lower in energy. The alcohol, if we pull the proton, again, those electrons that are left behind from the sigma bond sit on oxygen, but these electrons are not in conjugation with any pi system. So when they're left behind, they're just going to sit there in an sp3 orbital and they can't go anywhere. sp3 orbitals are going to be much smaller in volume than a conjugated pi orbital. And as such, these will be higher energy, more reactive electrons. These are going to be lower energy, less reactive electrons. And we see as a result, right, that the carboxylic acid will be more acidic and the alcohol will be less acidic. All right, just a couple more factors. All right, so this is a factor we call the inductive effect, or inductive electron withdrawal from nearby electronegative atoms. I just want to point out that this is different than just electronegativity. So when we were talking about electronegativity in factor 1, we were talking about the electronegativity of the atom that gets the non-bonding pair. Right? In this case, we're talking about the electronegativity of atoms nearby, but are not actually accepting the non-bonding pair. Okay, so here we have 4 different carboxylic acids. You can see the only difference among these 4 is as we go to the right, we're losing 1 hydrogen and we're gaining 1 fluorine, right? So this is going to be acetic acid. This is going to be fluoroacetic acid. This will be difluoroacetic acid. And then here we have trifluoroacetic acid. You can see the trend, right? Normal acetic acid is going to be the least acidic of these 4, whereas trifluoroacetic acid is going to be the most acidic of these 4. The role that the fluorines play is that they're able to delocalize some of the electron density that's going to show up on the atom that is accepting the charge, right? So in all of these cases, it's this oxygen that accepts the non-bonding pair and gets a negative charge. But what the fluorine is doing is it's pulling electron density away from this carbon, right? This carbon next to the carbonyl. Right? If we have 1 fluorine, right, we just have 1 fluorine pulling electron density away. If we have more, right, we have more fluorines pulling electron density away. So we can say that this carbon has a partial negative or partial positive charge because the bond is polarized towards fluorine. This carbon is going to have a larger partial positive charge because we have 3 fluorines now pulling electron density away from that carbon. Right? What this does is it kind of creates a gap or a void, right? So fluorine is pulling electron density away from this carbon. This carbon, because it's now electron deficient, is going to be pulling electron density away from the rest of the molecule. right? So if we adopt a charge on this oxygen, right, a negative charge on this oxygen, what fluorine does is it's kind of pulling the rest of the electron density from the molecule away from that oxygen, so that oxygen is going to be more comfortable with a negative charge, right? So if the electron density from these molecules is going this way, right, it's okay, or somewhat okay, to have a negative charge and an extra pair of electrons on that oxygen, right? The analogy that I usually give in class is if I have a bungee cord, and I'm standing in the front of the classroom, and I give the other end of that bungee cord to somebody in the first row, and I pull that bungee cord, that person in the first row is going to likely come towards me or be pulled towards me, right? And so that would be me being the fluorine and the student in the first row being this carbon, right? Now imagine a scenario where I have the bungee cord in my hand and it's passed to somebody in the front row, and then that person in the front row has a second bungee cord and they pass it to somebody in the back row. Now when I pull on my bungee cord, that person in the front row is going to come towards me, and as a result, the person in the back row is going to move towards the person in the front row. Because these are bungee cords, the person in the front row will probably move more than the person in the back row. All right, and this is really all to say that the inductive effect really drops off the farther you get away from the atom with the non-bonding pair, right? So you can see these fluorines are 1, 2, 3 bonds away from the atom that will hold the lone pair. Once we get to 5, 6, and beyond, the inductive effect doesn't really play that much of a role. All right, so the further you get away from the atom with the non-bonding pair, the less the inductive effect matters. All right, and then finally, we're going to go over the conjugative effect. And this is one of the more confusing things that, one of the more complicated things, or one of the things that's harder for students to understand. But it's really a matter of how other groups are going to influence the stability of electrons through resonance donation or resonance withdrawal. Okay, so here you can see we have 3 carboxylic acids. This is benzoic acid. This is 4 methoxybenzoic acid, so there's a methoxy group here. And then this is 4 formal benzoic acid, so there's an aldehyde group or a carbonyl group across here. Right? Benzoic acid is going to be have a pK of 4.2. You can see the methoxybenzoic acid has a higher pKa, right? So it's less acidic than benzoic acid, right? Whereas the benzoic acid with an aldehyde has a lower pKa, so it's going to be more acidic than benzoic acid, right? So 4.2, less acidic, right? And then more acidic. So let's take a look at what effect these 2 groups have, right? So in benzoic acid, that's just a hydrogen. We're not going to worry about that. All right, here we consider a methoxy group, or an oxygen with something else hanging off of it. We consider that an electron donating group, right? So you can imagine if we have an electron donating group, we can take those electrons and then push them into the ring, right? And we can put that pair of electrons on 3 different carbons around the ring. But the most important one, or the one that explains this effect, is going to have that negative charge, that lone pair, next to the carboxylate group. Okay, over here, this aldehyde we consider an electron withdrawing group. And so you can see how it's conjugated with the ring. So the way that it's conjugated with the ring, right, we can take electron density out of the ring. Right? And what that does is one of the resonance structures shows that we have a formal positive charge next to the carboxylate group. Remember, the carboxylate group, when it loses a proton, is going to have a negative charge distributed between these 3 atoms, right? Or sitting on either of these 2 oxygens, right? If we're putting more electron density in that area, that's going to significantly destabilize the electrons that are left behind. Right? In contrast, if you look over here, what we're doing is we're pulling electron density out of the ring, right? That puts a formal positive charge on this carbon. Now we have a negative group, right? Or a group with an extra pair of electrons sitting next to a positive charge, right? We can't donate the electrons into that carbon, right? These are not in conjugation with that carbon, but the fact that we have something that's negatively charged, right? Something with an extra set of electrons next to a positively charged atom, that's a good thing, a stabilizing effect. And so we would see that as the most acidic of the benzoic acids, right? And then the methoxy as the least acidic of the benzoic acids. Right, so those are the structural features that can influence the acidity of a molecule, right? Or more specifically, influence the stability of a molecule's conjugate base. Right, the final thing that we're going to go over in this chapter is looking at how we quantify acid-base equilibria. Right, so here you can see that we have an acid-base reaction. So I have isopropyl alcohol, and that's going to be reacting with hydrogen cyanide. Now, when we look at these two molecules, you can see that isopropyl alcohol has a proton, right? Just like hydrogen cyanide has a proton. So the question becomes, if both molecules have acidic protons, which will serve as the acid in the reaction, right? In this case, it's going to be the molecule, or in all cases, it's going to be the molecule with the most acidic proton. That will be the acid. So when we look at these two molecules on the periodic table, alcohols have a pKa of around 16, right? And hydrogen cyanide has a pKa of 9. So as a result, hydrogen cyanide will act as the acid, and the isopropyl alcohol will act as the base. If we draw the acid-base mechanism, the lone pair on oxygen is going to reach out and grab a proton from the hydrogen cyanide, and then the carbon-hydrogen sigma bond is going to break, and those sigma electrons will be returned to carbon. So in the product, you can see that we have our new OH sigma bond. Oxygen gets a formal positive charge, and it loses a lone pair of electrons because now that second lone pair is wrapped up in this sigma bond. All right, and then hydrogen cyanide just becomes a cyanide anion, and the CH sigma electrons are now isolated to carbon, and carbon gets a formal negative charge. All right, it's important to point out that some molecules, or a lot of molecules, like this alcohol, can behave both as an acid and a base, right? So if we have a strong enough base, right, this alcohol will lose a proton, okay? If we have a strong enough acid in solution, the alcohol will act as a base, and the oxygen will get protonated. Okay, second question is, which way will the acid-base equilibrium lie? Which direction is this reaction going to favor? Is it going to be product favored, or is it going to be reactant favored? All right, and so we just have to remember that the equilibrium of an acid-base reaction will always favor the weaker acid-base pair. All right, and if we look at this acid-base reaction, we're starting with an acid with a pK of 9. We're ending with an acid with a pK of -2. The higher the pKa, the weaker the acid. The lower the pKa, the stronger the acid. Right, so if we look at the acids on either side, the hydrogen cyanide is going to be the weaker acid. All right, and then the protonated alcohol is going to be the stronger acid. So as a result, the equilibrium is going to lie to the left. This is going to be a reactant-favored reaction. All right, and then finally, how can we determine the equilibrium constant of an acid-base reaction, right? So we're actually able to quantify an acid-base reaction and determine, an approximate equilibrium constant that tells us in a reaction how much of the products are we going to have versus how much of the reactants. All right, so since pKa is really just an expression of an acid's equilibrium in water, we can use the pKa's of the acids in the reaction to calculate or quantify the equilibrium constant, right? And so when we look at this, the two acids that we are using, and I did this wrong. There we go. Two acids that we're using are going to be hydrogen cyanide and the protonated alcohol. All right, and the way that we calculate the KEQ is the KEQ is going to be 10 to the pK of the conjugate acid minus the pK of the acid. All right, so this is conjugate acid, this is acid. All right, in this reaction, the conjugate acid has a pK of -2, the acid has a pK of 9, so the KEQ would be 10 to the -2 minus 9, or the KEQ is 10 to the -11. Took the wrong pKa when I wrote this up originally. All right, and so what this indicates is that this is going to be a heavily reactant favored reaction, right? KEQ is less than 1, all right? If the KEQ was greater than 1, we would say that this was a heavily product-favored reaction. Okay, it's important to point out that pKa is a logarithmic value, right? So a pKa difference of 1 is going to be a factor of 10, right? So if you have a conjugate acid, if the difference between the acid and the conjugate acid is 1, there's going to be a 10-fold difference in the amount of the weaker acid versus the stronger acid, right? For a pKa difference of 2, that is a 100-fold difference in acidity, or 100-fold, 100 times more acidic. For a pKa difference of 3, that's going to be a factor of 1,000. pKa difference of 4, it's a factor of 10,000. So it's important to recognize the logarithmic nature of the pKa scale, right? So you can see the difference here, pKa of 11, 10 to the -11th or 10 to the 11th, depending upon which direction you're going, right? That more or less takes us to the end of acid-base chemistry. We'll probably pick up some of these concepts again as we go through chapters 7 and 8.